was amazing meeting all these people from all these places who've been facing similar problems as me or as the company. And it's nice just talking to people in the hallways after the talk, during talks, between talks.
Okay, everybody, welcome. My name is John Lakos from Bloomberg, and I'm here to help. Seriously, I think people who are coming to this talk have some concerns about C++. How many people who are at this talk are nervous that C++ is in need of a little bit of love? That's more than a plurality. That's a majority. So about 3 years ago, it became clear that somebody needed to do something. And I started Break Glass, Pull Lever at my company. And at the time, it seemed like, what? C++ is perfectly fine. We use it all the time. It's not broken. What's wrong? But there was a trend. And unless you're on the ground and really know what's going on, you might not see it at the highest levels. So this talk is the genesis of that. And what I intend to provide here is a lot of history, a lot of currency, and then a goal of what we need to do to make the title of this talk true. And there's a little bit of a double entendre. What does the talk mean? What does C++ need to be safe? What does it need to be safe to use? What does it need to be safe from Rust? Both, really. Because for people who are really invested in C++, for example, Bloomberg, and let's be honest, Google and Microsoft and Adobe and all of these people have millions and millions of lines of C++. Going to another language is a problem. So we need a solution that preserves the trillions of dollars of software capital that exist in the world today and incrementally make it better while we seek for the perfect solution. So that's what this talk is about. I'm going to just try to bring you all on board, and hopefully that'll work. So there's a lot of bureaucracy in the world. You can see by the layers of the slides that I put up for the different organizations. The abstract is here, but you don't need to see that. The only thing I want to emphasize is the green on the bottom line, which is we're going to talk about C++ 26 and beyond. Introduction and motivation. You all know this. C++ has come under criticism. Rust is out there saying, look at me. You know, regulatory agencies are saying, hey, why are you guys writing in a language where the thing can just run off a cliff? Government and cybersecurity organizations are legitimately saying, we've got people who don't even have a degree in computer science writing highly secure code that could have race conditions. Like, who allowed that? That's crazy talk. So people are moving away. Google, Microsoft, and Adobe, they don't want to. But imagine if you're Adobe and you have all of these people writing multi-threaded code. And the multi-threaded code, it can't just corrupt the whole system. Now, some systems, if there's a problem and it doesn't do what you want it to do, something blows up. But in other systems, if it doesn't do what you want it to do, it's not so bad as long as it doesn't provide a security hole or corrupt the entire system. In other words, that it's contained. So people have different understandings of what safety means. And I've had a lot of people read my slides and coach me to help me understand the difference between the way I think and the way other people think. Everybody thinks about this problem differently, and that's why people talk across each other a lot. So our top-level strategy to get C++ back on track is to reinvigorate it. That means all of the companies that have been walking away from C++, they're walking away because they don't think C++ has a future. We think it has a future. And we know how we need to do it. Specifically, we want to make it more safe, healthy, and efficient. I picked these names after a lot of thought, and there's only one acronym that makes sense, and it's the right order. Okay. Three primary areas of focus. Safety, oh my goodness. Correctness. To me, as a software engineer at Bloomberg, correctness matters. Security matters. Those are two things that matter. If somebody can poke a hole in your program, it's not correct by our definition. But even if they can't and you get the price wrong, it's not correct. And a program that has well-defined behavior that does the wrong thing is incorrect by my definition. Not everybody agrees. It's not safe. By my definition, safety includes correctness. Some people do not do that. I just want to make it clear. Health. The ecosystem needs to be supported. There are many ecosystems that are much, much more rich than C++. But even the ecosystem that we have, if people aren't putting money into implementing it in compilers, we have a problem. And then there's two kinds of efficiency. C++ has to be second to none in efficiency. Nothing gets between C++ and the metal. And human efficiency. We want C++ to be efficient. And so in terms of development, and there are many things that we do right now in C++ that are not that efficient in terms of development, yet super efficient in terms of performance. So making C++ safer, correct. What does that mean? The essential behavior is as intended. Essential behavior, remember that word. That's the behavior that's in the contract. I promise if you satisfy my preconditions that I will do this for you. Okay? So we also want to detect any defects. I mean, that's part of the goal of making C++ rich and robust and secure. And then we do have a defect. We don't want somebody to be able to go and poke into it and do some very evil things. But that's a different mentality. As a pure academic, I could write a really wonderful hash function. It's perfectly correct, and yet it could submit to a denial of service attack in an environment where it's set up, exposed to that. So you have to ask, is security important? In most cases it is, but it's not the same as correctness. Okay. Making it healthier. We just want to make everything healthier. And I'm going to skip over this fairly quickly because this is not important. We just know we need to pour money into C++ to make sure it's caught up. And then efficient. Again, the programs need to run fast. So everything that we do, we can't slow it down because we want it to be safe. There isn't a contradiction between runtime efficiency and safety. There is a contradiction between runtime efficiency and runtime checking. I just want to point that out. There is a good world, but you have to look at it a little bit like this, and then it's a good world. It really is. The human efficiency is, and I think AI might be coming into this, we might get a lot more human inefficiency by just making the boilerplate code that we have to write a little less tedious. And there's all kinds of ways we can do that in the language. What we aim to achieve is make C++ easier to use securely and correctly, close the gap with safe languages, blunt the desire to migrate away from C++. If all of you knew right now that C++ 32 would be just as safe as Rust, would you really be so excited to run away? Think about it. Improve the typical user's experience. Yes, that is the goal, but not at the expense of giving away needed performance. As long as you can get it back, that's good. We want safety, but not at the expense of needed performance. So default to be safe, but be able to get it back. I think everybody agrees this is the way C++ was designed. I hope so. And this is important. I want to set an example for other organizations. So everything that you're about to see in this talk, we started, but we want help. The purpose of this talk is to get companies who actually want C++ to thrive for the next indefinite period. We all should pitch in like NATO and get it done. Seriously. Doesn't have to be 5% of your GDP, but it should be something. It really should be, even if you're volunteering. This is medium to long term. There are people that demand that we get results in the next 6 months, 1 year. That's not how it works. And I need to show you some stuff about how the standard works. So this part of the talk is how the sausage is made for real and how we want to get it made better. That's why you're here. By the way, a shout out to Sherry Sontag, reviewed this with me yesterday, and the one comment she made was, tell people where they are and why they're here and what they're about to learn so that they don't start looking at their phones. So I'm telling you now. Timur Dummler back in ACCU wrote this little caricature of what happened with contracts in the standard. And it's a very, very cool little chart, which I'm not going to go over, but I am going to animate. So somebody had an idea back a long time ago in the Stone Ages, and it died. And then there were a lot of papers written, and then the papers stopped. And then I submitted a paper on something that I thought was a good idea. It was macro-based. And somebody else had some alternate ideas, and then they both died in plenary. And oops, sorry, but very bad. So then we started a new one, and Bjorn Strustrup was on board because he thought this was very important. And lo and behold, we made some progress. We got the proposal into the C++20 working paper. And then we got it taken out in 2019 because a lot of people weren't so sure that we got it right. And then we started SG21, which is the contracts working group. And we worked really hard, and we got this proposal. And then we got it through the EWG, and finally in February of this year, we got it into the standard. And we made it through one plenary cycle without taking it out. This is good news. We're optimistic this time because many people believe that this particular feature is the most studied, most principled, most mathematical, most demonstrated, just most anything you want to say, correct feature that ever was entered into C++. I don't say that lightly. I'll explain why I think that. We are here. And by the way, Herb's talk on Monday was nothing short of brilliant. He had a few concerns that I don't. Modulo that, perfect. And it was very motivating. And he covered a lot of material. And if you missed his talk, please go see it. Now, on the back end, I invented what is now contracts in 2003, myself, at Bloomberg. In 2004, it started being used all over Bloomberg. And then in 2009, I took it, I said, you know, this is really, really good stuff. Let me productize it and give all kinds of usage examples and make it really available. And then, what, did I go the wrong direction? No, here we go. Here we go. And then we open sourced it. Then, in 2014, we discovered something, that if you have to crash your program when something goes wrong, then you can never add contracts to legacy code that's running. You can never do it because you put it in, the program crashes, and you lose money. You can't just observe it. So we realized that our system had now gotten to the point where it was being used so much, we needed a new semantic called observe, which is why assert is no longer good enough. That's why. This is the kindergarten introduction to contracts, but just understand, it is a deep subject that is so easy to use. It's like a car that drives itself, but building that car is, okay? So we're going along. Anyway, in 2020, there's a lot of reflector traffic. And then in 2022, Bloomberg realizes that we need to start taking a lead. Now, this is not to brag about Bloomberg. We noticed that we started being helpful. And you'll notice that we started sponsoring open source environmental things. And eventually, we actually had a conference on safety. It was at the beginning of this year, which we arranged. And then finally, and this is from our CTO, Sean Edwards, we are planning to support the ecosystem and prototyping new features going forward. This is a very important statement by Bloomberg, the CTO. So, we're serious. That's what this whole talk is about. Now, let's look at the timeline. What happens when you get an idea? This is what actually happened. You get an idea and it blows up. Okay, fine. You get another idea, it makes it a ways. Whoa, it makes it into the standard. You start prototyping it. And the prototyping keeps going. But then something happens and it gets taken out of the standard, so that whole proposal dies. We get another idea, and it goes on for a while, but the prototyping pays us back. That's what got us a lot of advantage, because the prototyping showed us that the ideas in C++20 were really good ones, not perfect. There were a few bugs, but almost exactly the right idea. So we took what we called a minimum viable product, shrunk it down, which grew and grew and grew and grew and grew back, but not as big as it was before. And that new thing, 2900, was prototyped and made it into the standard in February of this year. Hopefully this stays. Then eventually it'll make it into the annual compilers, and hopefully we're good. Unfortunately, because every company is way behind in using the new compilers, by every, I mean every large company that isn't like really on their game, they'll start 4 years from now. So if you look at this, this is how unappealing it is to be in the standards committee. You get an idea, it fails a number of times, then it finally gets to someplace 5 years later, then a year later it gets into the compiler, and then 4 years later it gets into production. If you're a manager, are you going to send me to the standards committee knowing that 10 years later you might be retired and maybe I got you something? So this is just that, but it's reality. Could we do it better? This is just ongoing prototyping, by the way. Could we do it better? How about canonical? What could be like a little bit better? Well, we get an idea. We think about it. We start doing compiler prototypes, and we prototype them until we get something into the standard. And then it's in the standard, yay. And then the next year it goes into the annual compiler versions, and let's say we're on our game, we've been paying attention because we haven't been waiting with that delay, and maybe a year later we're in production. This seems like a reasonable goal, but we can do better. What Bloomberg wants to do, this cuts it to 4 years. We can shave off 1 year by, when we get to this point, immediately put the prototype, even if it's not production ready, into the compiler, into the used compiler, so they can be used against the current code to get the code ready so that when the release happens officially, done. And that means 3 years. A 3-year cycle that's just one delayed from the 3-year cycle of the committee is not great, but I don't think we're going to be able to do much better. All right, I took a lot of time to explain that. I'm going to probably have to speed up a little bit, but I just wanted to make sure that the beginning part, everybody understands what we're doing. We're trying to frame what's going on. What does it mean to be safe? It means a lot of different things to different people. And I'm just going to put this out so you can read it, because you can read it faster than I. This is something that I want to talk about. Surprisingly, correctness isn't considered part of safety. As long as you want to drive your grandmother home, as long as she gets to some house, it's good. Doesn't have to be her house. Just don't let her have a flat tire. And if she has a flat tire, don't let it blow up the car. I must take a pause. Okay. So I believe that correctness is an integral part of safety, because if I get a price wrong, we have a lawsuit. What is memory safety? Has anybody ever heard the term memory safety? I'm expecting a few hands. Good, that's about what I expected. So memory safety, a language is memory safe if it does not permit access to unallocated or uninitialized memory. Seem good? Can somebody find a flaw in that? Because there's going to be somebody in here that goes, wait, but.
What about type hunting? It's allocated and initialized, but incorrect still.
How about this? You're right. Am I okay now?
No.
What? What's next?
The wrong memory. You're accessing something that's all the right site, it's allocated, it's initialized, but it's the wrong place. You access D instead of A.
That just sounds like it's incorrect.
You're right.
But that's not memory safety.
You shouldn't be able to access a neighboring array by going array out of bounds.
Okay, what was just said is, you're right. If you have, you're absolutely right. So there's an inch more to this, and on the next iteration of slides, I will try to make that point. The point being made is, the language, if it's memory safe, shouldn't allow you to index outside the bounds of array that happens to land into a properly allocated or initialized. I think I was cheating by saying that that was the type stuff. Maybe I wasn't. Understood. So these are garbage collected languages. They solve the problem by not letting memory go away. Functional languages don't let it happen in the first place. Languages that enforce the law of exclusivity, Rust, lifetime borrow checking, and Swift 6.0 happens to use reference counting. The same idea for avoiding race conditions, but Swift, as I understand it, gives you a little bit more breathing room when it comes to the algorithms you write. Now, I'm not a Swift writer, not a Rust writer, been studying it, but the methodology they use is automatic reference counting, which is different from compile time exclusivity. So we'll just understand that for most purposes, Rust and Circle and Swift do the good deed of making things memory safe, where Swift gives you just a little bit more oxygen without doing anything else. I'll explain that. Okay. What memory safe isn't, and this is important because memory safe has often been told, John, memory safe is like, that's good. Is your ice cream memory safe? No. Memory safe is not this. It doesn't imply the absence of all undefined behavior. And so, for example, in this wonderful example, we have this thing that's going to overflow an int. And integer overflow is UB, but it's not a memory safety issue per se, right? Okay. So what are we trying to achieve? Now, this is the big print. Remember that everything I say in this talk is what we're trying to achieve, except what we've already done. I'll show you what we've already done. I'll show you what we could do, and I'll show you what we're trying to achieve. So security. Every C++ program can be built such that no core language UB is ever executed. That's what we're trying to do. User-defined functions can be written such that the plain language contract, preconditions and postconditions are optionally checked redundantly, typically at runtime. We're trying to do this. And there's a little asterisk. And this is part of the engage, entertain, and educate where I engage. Not all plain language contracts can be checked at runtime. They're for the human being. Can somebody name something that emphatically cannot be checked at runtime? Complexity. Okay, imagine I'm talking about a precondition. A precondition for a function that cannot be checked at runtime.
Function.
What?
The function halts.
The function
returns.
The function return. It can't be checked at runtime. Okay, so absolutely it can, because that's what a postcondition is. We can check what it returns. I'm thinking about something that you couldn't check.
Exactly. That it will return. You can't solve the halting problem at runtime.
Okay, so suggested, you can't check. Here's what I'm trying to say, that I want to check that no undefined behavior is executed as the result of a precondition that isn't satisfied. In other words, you see what I'm saying? I'm a function, and I'm saying, is there something where you're going to give me an argument and I can't check it at runtime? There's no way. Okay, it depends on how much information you have. If you have enough information, you can check everything. I just want to point something out. This is not a trick question. The more information you have, in theory, you can check anything. What you can't check is something that's outside the program. Like, has your CFO signed the license to your vendor that you can use the function? That's not something you can check in a program. But anything that's in part of the program, you get all the source code, you get everything else. In theory, I didn't say in practice, in theory, check anything. Okay, but that's a different story. The halting, does it halt? No, but did you give me, like if you pass in something and says the precondition of this thing is this function halts, that's a good answer. I like that. I'll remember that, thank you. This was good. We may not get through this talk, but that was good. What are we trying to achieve? Okay, we're trying to achieve that without any source code changes, we don't execute UB. That's what we're trying to do. Without any source code changes, no source code UB will ever be executed. That's what we're trying to do. Okay, we want to provide the tools so that, but besides just the standard library, you can do it yourself. And that includes third-party libraries. So basically all the code except that little bit of code you write in your main has all of this beautiful stuff already there. And I'm sure everybody here, they never write anything but just a few lines of code to reuse their reusable libraries, right? That's the goal. That's what we do. No change to client code. What's the biggest problem with Rust and Circle and Swift? You would have to change your code. A heck of a lot, right? You'd have to rewrite it. Ick. What if you didn't have to rewrite your code? What if all the code you'd ever written now gets checked? And let's say it doesn't get checked 100%, only 99%. Well, guess what? Rust doesn't catch signals. Oops. Anyway. So these are the tools, the 6 tools that we know about that address UB. Runtime contract checking error, erroneous behavior, symbolic contract assertions, source code subsetting, previously known as profiles, compile time enforced exclusivity, and runtime enforced reference counting, which used to be runtime enforced exclusivity, but it turns out that I'm trying to model the different kinds of things we have, and the compile time exclusivity is what Circle and Rust do, and the runtime exclusivity is more like what Swift does, even though it does the race condition checking exactly the same way as Circle does with the bar checker. So these are the 6 things we're going to quickly talk about, I hope. What's a contract? Plain language contract. It's a natural description of what agreement between clients and libraries. Contract assertion is C++ construct that identifies something that must be true in a correct program. Note, you put a contract in a program, whether you check it or not, it's a true statement, and an AI can read it, and a static analyzer can read it, and a human being can read it. It's additional information. The more information you have in a test driver, the more redundancy you have. The more redundancy you have, the better the test. So if I put 100 assertions throughout my code, they all have to be consistent, and an AI or a human being or a runtime checker can take advantage of it. So let it not be thought that having an assert that isn't checked isn't good. It's good. And then if you check it, it's better. But you have to check it all the time. Because think about it. You know, it's sort of a hideous description, but suppose you're having a very old house that had a lot of food in it, turn on the kitchen, and oh my God, look at all those things running around. So when you turn on the thing, the assertions, when they're on, they effectively check all the bugs. So then you fix them. Next time you turn on the light, there are a few bugs running around. Fix them. Next time you turn on the light, there's one running around. Next few times you turn on the light, there are no bugs. Yeah, like 2 weeks later, there's a bug. So fix it. The point is that the value of checking goes down with the checking. So the more you check, the less you need to check. And this is why the approach that we're going to take scales. Because with sanitizers, you have to check the whole thing. What we're going to propose is incremental thorough checking. And instead of doing one thing at a time the way sanitizers do, we're going to check everything in a small region of your program, and we're going to do it without breaking ABI. This is a research project. Okay. C++ 26 MBV feature for contracts. It has preconditions and postconditions. This stuff is all, you can learn this anywhere else. There are 4 semantics. Okay. A 5th semantic that's controversial but is awesome. Don't let anybody fool you. They were scared, is assume. Everybody knows, right, that if you do something nasty with pointers, it's undefined behavior, right? The compiler can assume you're not going to do that. If you call a standard function, like square root, if it had any UB in it, you don't even need to call it. The compiler can just go, oh, you're calling it with a negative number. Now, I know the standard square root doesn't have that. But if there's any UB in any standard function and the compiler can determine at compile time that that would be UB, doesn't have to call it and do time travel. So assume is part of the standard, it's part of the language, and it optimizes code. And the funny thing is when you have contracts, you can have code and you can observe it, enforce it, ignore it, or actually benefit from it by knowing that it isn't broken, so you can assume it isn't broken. But you do it in that order. You don't just assume it. Now it's cray-cray. You assume it after you prove it. Okay. I just told you that. Simple use case, and you guys know this. I'm just going to throw it up here. This is a function declaration. This is essential behavior. This is undefined behavior. And just for clarity, this is a plain language contract. Is that clear? Plain language contract. Everything is defined by the plain language contract. Everything. And that comes from here. And where does the test driver come? From here, through the plain language contract. Where does the code come? From here, through the plain language contract. They're all independent representations of something you all have to agree. When you put contract checks in, comes from here, not from the code, from here, and they all have to agree. If anything disagrees, ask your AI to find out if they disagree. Oh, they disagree. Great. We have to fix it. It's broken. Okay. So precondition, postcondition. This isn't a very interesting postcondition. Can we do better? Think about what a square root does. If you took the square root, you'd like the square root to be as close to the actual square root as possible, right? Okay. So recall we have this next after function. So what we kind of like to do is we like to say, whatever answer you give me, it's either the same number or it's a little bit below, but the next tick up is above. Or it's a little bit above and the next tick up is below, right? We'd like that to be true. It's not good enough. We'd like that to be true. So we can express that in a postcondition where we check both sides. We check if it's the same, if it's less than, if it's greater than. That's a lot of code. Could there be a bug in that? You bet. Postconditions are not my friend. Testing, unit testing is my friend. There are reasons to have postconditions when you have properties. You put those properties in the test driver and test them. You don't have to put them in the code. Never mind, that's another story. Now, because we've checked this, we have to do something horrible. Because we've checked a parameter, we've done something that absolutely makes me ill, we have to declare a by-value variable const. This tells the compiler that it's not allowed to change it in there. For non-virtual functions, it's all in the same thing, so it's kind of like, it's all in the family. But for virtual functions, you get that in the interface, and if you make something, put a postcondition check on a virtual function with this mechanism, you have to make spooky changes at a distance. I hate this. One of the reasons why virtual functions aren't yet in the standard. But we have a better way, we have another way to do it that doesn't cause that. We still have the worst case where all right, you're C++, you want to mess up your whole client, we'll let you do it, but we told you, we gave you another way. We'll talk about that. So that's just one ugly thing that's part of contracts, I'm sorry. Postconditions. We didn't have postcondition. By the way, is this postcondition good enough? Turns out it's not. Turns out that if you use this postcondition, it's possible this one is on this side, the one bigger is on the other side, but it's closer. What do we write? Well, I spent 2 months analyzing this problem. I kid you not, 2 months, because it's going to be part of the next volume of my book. And here's how you write it. We're writing it with a contract assert. It could be written with a postcondition and then just call it, but it's a lot of code. What we're doing is we're going to look at the delta, and we're going to say if it's less than, we want to make sure that the delta on the upside is not less than what we have. And for the moment, assume that it says, for the moment, assume that the above square is above x. Because it could be that we have something here, and then we move up one, and it's still below, but we didn't check that it was on the other side. So just assume that it is. And the same way here. Now I say, just assume that it's going to work. And then I give you this proof that it does work, because if what I just said were the case, the number would be negative, which is less than 0, which is less than the absolute value of the distance from the other one, which isn't 0, blah, blah, blah. The point is, when you write postconditions, you're writing code. It could have a bug. You got to get it all right. That's hard work. write test drivers. Don't do this. It's crazy talk. Okay. Now, it so happens that if you use the previous method where it checks the squares, in the subnormal range, it's horrible. But this one works very well in the subnormal range. You'll get within 1 tick. That's why it took 2 months. Okay, most important, usage. We want this on square bracket. We do this on square bracket on standard library implementations. We will get 65% of the security defects in the standard library. For that one thing. It's like, why are we even having this conversation? It's not part of the standard. It's part of the standard implementation. People need to implement their code so the undefined behavior goes away, and it goes away without having to get permission from the C++ standards community. It just goes away. And the author of the code gets to decide how much runtime checking they want to trade off for performance, and where in the program in 29, where in the program they're going to be able to trade that off. Why do we call contracts assertion ghost code? Anybody?
It's not the primary function.
It's not the primary function. What can assertions do? Can we depend on assertions in our everyday lives? Do we know they'll be there? So one of the things you must remember that assertions of any kind are redundant. And if you're depending on them for any reason, you're wrong. The code is broken. So ghost code is code that might not be there. You cannot depend. It can depend on you. It can't mess with your essential behavior, but it can depend on you. But you can't depend on it. Think of Casper the Friendly Ghost. Right? Might not be there. Okay. Another sip. So teaching safe contract assertion practice. Remember I said that contracts are very, very easy to teach. It's this simple. Don't do that. What do we don't do? No side effects. Has anybody ever thought that side effects in standard assert was something we really want? We want those side effects, do we? They happen sometimes, and there are reasons why they happen. One of the things about this code, this design is every single assertion is independently controllable across every other one. So the power set of assertions are valid. If you have a program, no assertions, if the program's correct, it's correct. Any subset of the assertions that are in the program are checked, the program is correct. If that's not true, the program is broken. And there are reasons for this, having to do with scalability well beyond what most people would ever deal with. Remember, I've been doing this for literally a quarter century. So I've thought about it, written many papers, many books. We lived it for 20 years. This is the right answer. There's no question this is the right answer. And as what was said in the AI talk, was it yesterday? Or is it the day before? Anyway, what was said was, if an AI can look at it, they can do something with it. Even if it isn't quite right, and a human being can look at it, even if it isn't perfectly implemented, even if there's some corner case that we still need to fix, get it out there. It's not going to get any better until people start using it. And quite frankly, I think it's darn near perfect, and there's nothing we would change now. We would simply add to it. There's another thing I want to say. If you have something that fixes half your problems today, and there's no reason they couldn't start fixing them today, why wait until they fix 80% of them in 3 years? That makes no sense. So we should start using them today. Again, sorry about the advertisement. The advanced discussion is you're not allowed to make any destructive side effects. What this gives license to is if you're writing pushback on your vector and you have a bug and you put a print statement in your vector and it says pushback called, well, that's a side effect. Do you really want the whole program to go into a tailspin because of that? No. So the answer is printing pushback was called is not an essential behavior of pushback. Nowhere in the pushback contract does it say that it does it or that it doesn't do it. So remember that things that it says it does, it must do, and things that it doesn't say it does must be handled by QOI. Means It would be bad QI for there to be profanities in every pushback that you pushed. That would be bad. So, a destructive side effect alters essential behavior. Essential behavior is implied by the plain language contract. So remember, essential behavior is implied by the contract, and if you mess with it in the assert, it's destructive. Okay? We're going to have some availability to do other stuff in 29. I just want to give you a quick highlight. We can enforce things right in the spot. So regardless of what anybody else says, this is going to happen. Something is very important to people. We've got you. We have this notion of audit that says, wow, this is an n-squared check. I don't want it in my program. Oh, wait, my program's broken. It's 4 a.m. Yeah, I do want it. The third one is instead of doing that horrible const thing, we can do a capture on a post condition. So you just say, just copy that value here. Done. No spooky behavior. And fourth, we can have a requires clause that says, everything that I want this to apply to has to have a cost function. If your type that you're passing in doesn't have a cost function, well, guess what? I don't care. It doesn't count. It's finis out. So that's something that's important for certain kinds of programming, and we've got it all coming. This is something very exciting. So if you look at this, does anybody remember Strustrup's talk? Remember he was talking about how we can check for arithmetic narrowing. But there was also another one for arithmetic overflow, right? In any case, there are things that happen in the standard library. And we could write a lot of code to check that. We have a bug in our code. We're going to check for the bug in our code. And when we find the bug in our code, we're going to throw an exception, let somebody else handle the bug in our code. This is nonsense. We get that for free with simply turning on a switch that says, I'm checking that at runtime. No. And then you can tell the handler, do this. But you should never have had that bug there in the first place. Because if you can put code into your function that will cause an overflow, then your function is broken. You need to protect it with a precondition that says I handle numbers from 1 to 2,767. And that's it. If you go to do the data, I'll have a bug, so you can't do that. So that's nonsense. You don't have to change your source code at all. Look at this paper, P3100R4. We're implementing this. This is happening. So everything that you heard about that is unnecessary. It's extra code, it's error prone, it's a source of bugs. We're not going to wait. Core language does not, the standard library doesn't have a say in what we do with undefined behavior. So we're just going to make it available. You can just check your code and it'll just check it. What? You mean I can just have it check my undefined behavior? Today? Well, soon, as soon as we get it in. But yes. What do you think of that? I think this is just way cool, very relevant, and very current. We need to think along these lines. Write code that's correct and have automatic ways of determining when you fell off the boat. But not kill your program. Allow it to continue until you fix it. But fix it. This is the future. Erroneous behavior. This is another technique that we use. This is more about security vulnerabilities when we're not actually doing the expensive checks, making sure that something happens. Importantly, the use remains correct. Uninitialized reads was the example. We were just going to say, anytime you put an int on the program stack, it's going to be 0. But that would hide intent. That would create bugs that you would need a human being to determine rather than a sanitizer. We said no. We're going to create a new kind of behavior called erroneous behavior, which is just like undefined behavior, except it's defined, but it's still wrong. But you can't time travel off of a bug that's erroneous. Enough said. This is an example of it. Anyway, I'm going to have to speed up because I got only 15 minutes, but I think it's gone well so far, so I think I'm making some good points. I'm good at speeding up at the end. I give 5-minute lightning talks for whole hour slides. But the point is, we have this nice Venn diagram because we can either check the preconditions on the integer overflow, or we can just give it some behavior. We can do both. We will do both. That's what Rust does. But there's other things. So the rest of these are kind of less important because they're really not going to happen. Something else is going to happen. So I'm going to go through quickly. If you don't follow, it's no problem. Core language example is begin and end. And look at this. This is one of those things where we're passing in two different arrays. They need to be contiguous memory. So if we put in this pre-symbolic, it's just a symbolic thing. It tells the client compiler, hi compiler, this has to be true. This is a simple case. It isn't going to work in all cases, but it's true. And now the client compiler just observes this and goes, no, nope. It's just an example. So a standards example, it's the same idea. I'm just going to put it up so you can see it. Same idea. But a harder example would be if there's some runtime code going on in the middle, might obscure it. So this is where stuff gets to get hard, and this cute example falls down. You see that? What's happening is there's some runtime stuff going on in the middle. And compile time stuff doesn't work well when runtime stuff goes on in the middle. Okay? Profiles, very quickly. Has anybody ever heard of epics? Vittorio stuff? So profiles are just a way of what they are now, is subsetting the kind of C++ you'd like in your house. Don't put this in my house. It's too dangerous. And that's really all it is. You put this in, and it's an error. Nothing to worry about, nothing to see here. It's just another technique. Exclusivity enforced at compile time. Here's several hours, here's a day talk. We won't even talk about it. The law of exclusivity, in a nutshell, well, I'll leave it up for a second. The law of exclusivity in a nutshell is basically saying you have one writer or some number of readers and no writer, basically. And it's enforced at compile time by something called a borrow checker in Rust and Circle and Swift. So here's an example. This is ill-formed because even though there's no likely chance there's going to be a problem, there could be a problem and none of the compilers are smart enough. We could reserve a bunch of space. Now we know there's not going to be a problem. By the way, in case you didn't know, the for loop binds, it doesn't keep growing. It's not one of those things. I learned that. It's done. So there's no infinite loop here or anything like that. Anyway, doesn't help. So Circle and Rust won't deal with this, but a solution that was based on garbage collection or automatic reference counting like Swift could possibly deal with this. So it's a little bit more air. Okay. Reference counting enforced at runtime. That's sort of the thing. So my boss's boss told me about this thing called box data, which is not optional. And I wasn't able to find it online. I've not found anybody else who's talked about it. But it makes sense because it's data that's in the box. So I'm good with it. So box data is essential behavior. And what it does is it keeps track of stuff that isn't part of what you should be keeping track of it, but it's going to keep track of it for you. But it's necessary information. And so the same thing that we saw before works fine. And this time, by the way, I forgot to mention on the other one, when you're using a compile time exclusivity, you can't use the standard library because it's not designed for that. So I failed to mention that in the other one. I'm mentioning it now. Compile time exclusivity, we need an SDL2. Here, look at this. We don't need an SDL2 for this particular property. And we don't need to declare it safe. It's not special. So that's good. The other one, we had to declare it safe. This is a safe region. It's using safe code, blah, 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 blah. Sorry, I forgot that. But you can go back on the slide and look. That one has to be SDL2. That's one of the reasons we can't use it. And this is another example of iterator invalidation. Oh, I'm going to have to go through this fast. This is inherently not compile time checkable, but it still can be done with reference counting. Now, this is important. If you don't want the problem to happen in the body of the code, Just put a precondition on it that doesn't let it happen. Now you'll never have a bug in the body of the code because at the call site with the precondition it goes, oh no, we don't accept that, sorry. And then the client will know where the client went wrong. Because you'll say in your plain language contract, don't do that. Preconditions guard UB. Cannot invalidate UB. B cannot be invalidated. Okay. Ghost data. Okay. This is the punchline. Optional information made available to multiple contract assertions at various granularities, e.g. all assertions within a particular function invocation that would not otherwise be representable in the abstract machine. Here's a unicorn for you. Imagine you're able to transmit sufficient information across translation units without changing the ABI, such that there's enough information locally so that you can detect all UB. That's a unicorn, right? Doesn't exist. Maybe it does. I am not promising you that we are going to be able to solve all UB by 2032. But I'm going to promise you're going to try. We do have a plan. Just saying. Why do we call it ghost data?
It may not be there.
Yes, it may not be there. And when it's not there, it costs you nothing. This is the important stuff. What we're doing is we're doing the analog to contracts. In fact, it's contracts on steroids because the framework of contracts remains the same. We're going to add more information under the covers so the contracts become more powerful. It's like putting a supercharger in your car. Now we can check more than just array bounds. Now we can check lifetimes. Now we can check data races. Now I had a long talk with Timur, and he kind of put a little bit of the kibosh on me. We have all kinds of sanitizers that do this. They do it at a global level. But even sanitizers can't check everything. So if you don't have sequential consistency, your sanitizers will have bugs. But the thing is, if you're writing code that doesn't have sequential consistency, then you better have a few smart people looking at it and stop relying on a compiler to check your code. I mean, oh my dear God, that's a very, very, very small crowd, and there's so much other code out there that could be checked automatically. Let's not let the tail wag the dog here. I'm just saying. But anyway, so it's not 100%, I'm going to say it right now, but neither is Rust because it can't handle signals. So we have to accept an incremental improvement to something that's darn close to perfect. It's an active research project. These are the people that are working on it. Since I have only 7 minutes, I'm just going to go through the slides so you can see what's going on. This is the important part of the talk, and the rest of it really isn't. Current safety projects, just to give you an idea, the vector array is 65%. Contract violations from the written stuff is, that we might do on our own code is another 20%. We might get 10% from erroneous behavior. And then there's other things like lifetime and what else? Data races, and finally signals and crazy stuff that happens outside our control. The point is that we're going after the big stuff now, but we're not going to stop. We're going to go after all of it. So this is really the takeaway slide. We've got all these things. And the point is that ghost data is maybe, it's the scope of everything. The runtime reference counting is a little bit more air over the compile time exclusivity because it can do a little bit more, but it's the same kind of safety. What we're talking about with ghost data is that we're going to check everything that we can at runtime. Everything that can, in other words, our goal is to check everything at runtime, but to the extent that we have enough information where people have written their code in such a way that it would have been able to have used a borrow checker, we want to incrementally reduce the amount of runtime code until it approaches and reaches the amount of runtime code that would be if a borrow checker had been used. I'm trying to say that just right. So it's a continuum. The more information we have, the more we know, the more annotations we have, the less runtime data we have to preserve. You can think of it kind of like a compiler where it's reading a line of temp tokens, and it sees these tokens, and it reduces it to a higher level symbol. And when it can do that, it gets rid of that runtime. It reduces it to a solved problem. And we want our system to do that pretty much the same way. Anyway, I'm going to fly through the slides because I want to be done by my time, and I think this was a good thing to do. Other projects we have bug fixes, not worth talking about. I'll just put this up. We're through the important part. Memory allocators, you know that's my thing, and we're working on making that automatic, but that's not at the very top of our priorities. Trivial relocation is important, and I'm going to put this up here very quickly because I think either you know or you wouldn't care too much. And what's wonderful about trivial location is it just widens tremendously the amount of objects we can put in a vector without having to do this churn of deleting and reallocating. Right now we can do it with simple things like structs. We can do much better now. And you'll just see this from this animation. This is what eligible means. And then as long as this property holds, it's all good. Now, this is the new world. No, this is the example of the old world. This is the new world. So we have the same thing here. And now what we've added is a magic word that says, I've got this. So what happens is, has no virtue, yeah. No, what? That's not true anymore. So this is no longer a candidate for trivial relocation. And now it is, because we have clause B. So you can say either you do it yourself, compiler, or trust me. So this is not a safety feature, this is a performance feature, but it's a big one, because now a whole class of types can, in the standard, without cheating, be trivially relocatable. Does that make sense? There are other implications as well. This is essential for expanding the set of relocatable types. So, and the good news is, no destructive moves are called, only byte copies. And then I need to make the nerdly comment that there are particular platforms where it's not strictly a byte copy. But anyway, non-trivial relocation, it's the same idea. I'm going to skip over this because I have no time, but I think we did well with the time we had. And relocation. And reflection. Okay, I'm just going to skip over this too. This is just a picture of what we're doing. I just want to show you the different projects we have. The black dots are the things we cover completely. The yellow is we cover it sort of, and the whites are, and the whites are, we cover it a little bit, but it doesn't matter. But these are the projects that we're working on, just so you have it. And summary and conclusion, we need C++, C++ needs us. We hear you. Somebody should do something. We are. North Star, this is important. Make C++ such that we can and want to use it 25 years from now. That's what we want. We want it to be a go-to language for high performance, multi-threaded computing. Doesn't have to be the, has to be a. Okay? We're not trying to hurt Rust. We're trying to help ourselves. Anybody who has a huge code base in C++ has no choice. They must rely on C++'s existence for eternity. There's more C++. The world runs on C++. So our top level strategy, you know this. This is our strategy. Contracts, erroneous behavior, right? Healthier bug fixes, C++ 26 conformance, efficiency. Allocators are for the machine. Trivial relocation are both. And reflections for the human. Now, I'm just going to show you these projects because I should. So this is the stuff we're working now. This is automatic. I'm going to take a sip. And I still have about 51 seconds left. I just want people to see that we do have plans. All right, so I still have 24 seconds left. These are the people that are working on it with us. I mean, we don't know for a fact how far we're going to get, but we know we're going to get a long way. And if we get close, that's all that matters. Join us. That's me. I still have 5 seconds left. So 3, 2, 1. Thank you for coming. And any of you are free to leave. I negotiated that I could have another 5 minutes if you had any questions.
Thank you for the talk, John. I'm going to be difficult. I'm going to be the devil's advocate.
You go for it.
You mentioned at the beginning that many companies are moving towards Rust. And you also mentioned that many companies are going to do this because they have huge C++ legacy code bases. But you also shown examples like Google and Adobe, which have huge C++ legacy code bases, but they are still moving to Rust. So my question is, does it make sense? Like, what is the reason why all this effort is being put into reinvigorating C++, as you mentioned, instead, for example, into improving the interoperability story between Rust and C++, and then moving to Rust while still maintaining C++ as a legacy subset of the code base? Is it emotional attachment to C++? There's something that is, in your opinion, fundamentally wrong with Rust that couldn't work for a company like Bloomberg? Or is there any major reason that maybe we are missing here?
Okay, it's a fair question. So let me start with this. For companies that are just starting out, Rust is a perfectly good solution. For companies that have enormous amounts of legacy code and legacy people, it's the other side of the coin. If you look at Citadel, if you look at Bloomberg, we have no interest in moving to Rust. Not because we're emotionally attached. We have expertise in those languages. We have software capital in those languages. Also, if we move to Rust, it doesn't help us not maintain the code we have already. The interoperability story between Rust and C++ is horrible, not only in terms of the runtime interoperability and the just sort of the mechanical interoperability, but the way in which Rust is written is a different mindset. Moreover, to get the kind of performance, the kind of things that you want out of Rust, you have to limit the kinds of code you write severely. And that has an effect on performance too. So the highest performance stuff is still going to be written in C++ anyway. And yes, we can, if you can use a what do you call it? A system where they all talk via some external sort of way, through an external system where they're all plugins. That's fine too. But when you're talking about stuff like Adobe, where they're actually really depend on that very tight coupling, you can't do that across Rust and C++. The interop is through like a straw. So the bottom line answer to your question is, it's not emotional. If I had a choice between Rust and Circle, I would take Circle over Rust and work to make that, because that interoperability is at least halfway there. But imagine if I had a solution where I could apply it to all C++ code ever written, turn on the checks, squeeze out all the bugs, turn off the checks, and just leave it. That's worth $100 trillion. That's all I can say. And I'm striving for it.
Sounds good. Thank you.
Hey, John, thank you. I'd like to propose a scenario and hear your thoughts on what the interaction might look like. So let's say perhaps I have a function calling a factory that's producing a unique pointer. In the factory method that produces a unique pointer, maybe I want to put a post condition that says it shall not be null pointer, because it's factory, it's supposed to produce something. And the function receiving the null pointer probably also wants to do its own check to make sure that the thing that it gets back is null pointer. So I could see a couple scenarios in terms of what that interaction should look like. One option might be, the contract in the plain language contract says it won't be a null pointer, so I won't check it, it's fine. That's the agreement. Option two might be, I'm going to check it anyway, because per your point and Herb's point as well, contracts should be redundant, and if I'm relying on it, maybe that's bad. Option three might be, I'm also not going to check it because maybe there's some standard library or compiler guarantee that if it is null pointer, it won't be that bad anyway, because some expected results will come out of that. What do you see that interaction looking like? And if I do check it, also in the receiving function, maybe I have two error paths for the same scenario because I have to deal with it. If it's the post condition, I have a scenario that checks for null pointer, and I also have the caller condition that checks if it's a null pointer.
This is, okay, I think this is the standard case of contracts. First of all, the owner of main gets to make all these decisions. So every application developer gets to be their own boss. Second thing is, you can identify in 29, not quite yet, but in 29, you can identify each and every situation and treat it as you need over time. Third thing is you have what's called a violation handler. The violation handler is called when what you claim to be true isn't true. And what was made, the point that was made, I think, in Herb's talk is the more sure you are that it isn't wrong, the better it is to check it. Because if you are wrong, oh my God. So what you do is every single checkable precondition that you have should be codified as such and then used as needed and depreciated over time, because once you've checked something 100 times in a program, not in a library, in a program, and you never see a defect, the value of checking it goes to zero.
From the condition, from the like post-condition standpoint, would you still imagine the interaction has a check from the receiving caller, even if the condition...
So the post-condition thing, as I said earlier, I'm a big fan of unit tests. You can do everything that a post-condition does in a unit test.
Right.
There are cases, very rare, where post-condition is a thing to have. That we waited till 26 on post-conditions is a shanda, to use my wife's terminology. We don't need post-conditions, we need preconditions. Okay.
Thank you.
Okay, thanks for the talk. I have a question regarding the compile time exclusivity. The examples you showed were part of Safe C++ with the circle compiler, and to my knowledge, this is no longer worked on, the proposals, I mean. So how confident are you that borrow checking actually will get into the Safe C++ and the standard C++?
Okay, the question is how confident I am given that Circle is probably not on the fast track for C++. Circle solves a different problem than I'm trying to solve. Circle solves a problem that says, if you constrain yourself to this subset of C++ with these new libraries, then I will help you at compile time make sure you don't have a race condition. That's that promise. It is absolutely useless for Bloomberg and Citadel because we have too much code that we rely on that doesn't do that. So it's not useful. It's useful for companies that are starting out with new kids that don't really understand race conditions. This will stop them from shooting them and their boss in the foot. So that's what that's for. One day, way along when my children are in old folks' homes, we may want to adopt Circle for the subset of people who are writing new code that need those guarantees. But today we have Rust for that, and I'm trying to save 40 years of legacy buggy code. Okay?
Okay, thank you.
Are we over? We got one more. Okay, good.
Yeah.
I think this is the last question because we've been going for a while.
Yeah, thank you for the talk. So my question might be a bit more abstract. So you have this nice plan about eliminating undefined behavior and coming to memory safety in the next 10 years, but it still feels like this is plugging 100 holes in C++, and it's not changing the underlying attitude of C++ that we have standard, we have behavior that is defined, and everything that we don't explicitly mention in the standard is undefined, and hence may cause problems when compiler decides to exploit that for optimization purposes. So like it feels like we are trying to validate inputs in order to avoid SQL injections instead of actually modifying something with our attitude and not embedding user input inside SQL queries, if that makes sense.
Well, there's two parts. First of all, I should have said this. Input validation is not a use for contracts. If you're validating input like, as you know,
Oh yeah, sure.
We just want to make that clear. That's a very important point. Your point was we're plugging 100 holes. That is exactly right. We have identified all of the holes. We have them all. Mm-hmm. We have a list. We are going to systematically, instead of having your program be consumed by the cookie monster, you're going to get told that's wrong. Mm-hmm. That's a beautiful thing. Now your program can either continue or it can stop, but it's on you to fix it. Mm-hmm. So I don't think it's the same thing as just putting fingers in a dike. I think somebody's come over and they're going to put a steel plate over the dam. Boom, there's going to be a switch that says checked. And you'll never execute UB again.
Okay, thank you.
Yeah. All right, I have to stop this. Thank you all for coming. I managed to survive my cold.